How can a mirror be polished to extraordinary precision, pass its main optical test, reach orbit, and still make every star look wrong? The answer is NASA's Hubble Space Telescope, and the most important part of this story is not simply that the mirror had an optical error. It is that the test used to judge the mirror gave engineers confidence in the wrong shape. Hubble's primary mirror was not rough, cracked, or randomly damaged. It was an extremely smooth mirror with a precisely formed figure, but that figure was not the figure the telescope required. The difference was tiny in physical terms and enormous in optical terms. In this case file, I want to separate the verified facts from the popular shortcuts, explain how a test can be internally consistent and still be wrong, and show why Hubble became one of the clearest engineering lessons about measurement, independence, and trust. Hubble was designed as a space-based optical observatory above the blurring effects of Earth's atmosphere. Its primary mirror, made by Perkin-Elmer, measured about 2.4 meters across. Light from the universe would strike that mirror, reflect toward a secondary mirror, and then be directed into scientific instruments. Everything downstream depended on the primary mirror forming the correct wavefront. If that first surface was wrong, every camera and spectrograph would inherit the problem. The mirror was designed within a spheric figure, meaning its curve was more complicated than a simple sphere. That shape allowed the telescope to bring light from different parts of the mirror to a common focus. Producing it required far more than polishing until the surface looked smooth. The manufacturer had to know, at every stage, whether the mirror's figure matched the mathematical design. That meant building a test capable of distinguishing an almost perfect surface from one that was almost perfect but subtly incorrect. The key instrument was a reflective null corrector. The word null is important. In a null test, the optical arrangement is designed so that a correctly shaped mirror produces a null result, essentially the optical equivalent of no remaining error. The test does not simply place a ruler across the glass. It creates a known wavefront, sends that wavefront to the mirror, and examines the returning light. If the mirror has the intended shape, the returning pattern should match the expected null. If it does not, the pattern should reveal where the surface needs further work. This is a powerful method because it converts a difficult shape measurement into a comparison against a carefully designed optical reference. But there is a condition hidden inside that sentence. The reference must actually be correct. The reflective null corrector contained optical elements whose positions and geometry had to be known with extreme accuracy. Investigations after Hubble's problem traced the incorrect mirror figure to an error in that test apparatus. An optical element in the assembly was positioned incorrectly, so the device generated a misleading reference. The mirror was then polished to satisfy that reference. In other words, the mirror maker was not simply ignoring the test. The mirror was being adjusted in response to the measurement the apparatus provided. The measurement was the problem. This distinction matters. It is easy to describe the event as a bad mirror passing inspection, but that wording makes the process sound more careless and more mysterious than the evidence supports. The mirror was manufactured to match the optical test. The test itself did not represent the intended geometry. The resulting mirror could therefore look correct to the primary measurement system while being incorrect for the telescope's actual design. The optical error is commonly described as spherical aberration. In a perfect version of the telescope, light reflected from the inner and outer zones of the primary mirror should be brought together in the right way. With spherical aberration, those zones do not converge to one clean focus. Some rays behave as though they belong to a different focal condition than others. Adjusting the focus can improve one portion of the image while leaving another portion blurred. That is why this was not something a simple refocusing command could remove. A star would not become a sharp point. Instead, its light would spread into a blurred pattern, reducing the detail and contrast that Hubble was built to capture. The error in the mirror's shape was very small, often described in public accounts as being on the scale of only a few micrometers. That is smaller than the thickness of many ordinary materials people handle every day. But optics does not judge an error by physical size alone. A tiny departure in a mirror's figure changes the path of reflected light across the entire wavefront. The same surface error is also encountered through the reflection geometry, so its influence on the incoming wavefront can be much larger than the visual size of the defect suggests. A mirror can therefore be impressively smooth and still produce a serious imaging problem if its overall figure is wrong. This is an important engineering distinction between surface finish and figure accuracy. A polished surface may have no obvious scratches and still fail to direct light to the intended focus, When Hubble reached orbit in 1990, its first images revealed that the telescope was not performing as designed. NASA and its partners analyzed the images and traced the pattern to spherical aberration in the primary mirror. The problem was not inferred from one blurry photograph alone. The behavior appeared consistently across observations and instruments, and further optical analysis identified the characteristic signature of the incorrect mirror figure. The later investigation into the manufacturing and testing process found that the reflective null corrector had been the central source of the misleading result. That conclusion did not mean every measurement connected with the mirror was worthless. It meant that the main reference used to shape and accept the mirror contained a systematic error. This is where the common version of the story usually stops. A test device was wrong, the mirror followed the wrong test, and Hubble needed corrective optics. That summary is accurate, but it leaves out the engineering angle I find most useful. The deeper problem was not merely that one instrument had an incorrect setting or misplaced element. The deeper problem was that the test sat inside the entire production chain. It was used to guide the polishing process, assess progress, and support acceptance. When the same flawed reference influences both the work and the judgment of the work, the process can become self-confirming. Each polishing step can make the mirror agree more closely with the test, while the mirror moves farther away from the real design. That is a dangerous form of consistency. Repeatability is not the same as validity. Imagine shaping a key while using a template with one notch in the wrong position. Every time you compare the key with that template, you can make the key fit the template more closely. The measurements may be neat, repeatable, and easy to explain, but the key will not fit the lock that the template was supposed to represent. The test has not disappeared. It has become a precise measurement of the wrong standard. Optical null testing is especially vulnerable to this kind of problem because the instrument is not a passive observer. The test optics actively transform the shape being measured. A small spacing error inside the null corrector changes the wavefront presented to the mirror and changes the pattern returned to the measuring system. If the test is interpreted under the assumption that the corrector is perfect, the mirror can be polished to compensate for the test's own error. The final result then contains an error shaped by the instrument. That is why calibration cannot be treated as a formality at the edge of a project. In a measurement chain, the reference is part of the object being built. The public record also shows that the situation was more complicated than one instrument giving one isolated reading. Other testing and review activities existed, and the later investigations examined why they did not resolve the contradiction before launch. A second null corrector and additional checks were part of the broader story, but the presence of independent checks does not automatically make a process independent. A check may use the same assumptions, the same reference, the same alignment logic, or the same interpretation. It may produce a different result that is then attributed to uncertainty rather than treated as a reason to stop. The verified lesson is not that nobody checked anything. The lesson is that the checking system did not isolate the central error strongly enough before the mirror was accepted. That distinction protects us from inventing a simple villain. The available evidence supports a chain of technical and organizational weaknesses, not a need to assign an unsupported motive to one individual. A useful question is this: what would an actually independent test have looked like? It would not merely repeat the same optical arrangement with a second operator. It would rely on a different measurement principle, a separately traced reference, or an arrangement whose likely errors were different from those of the primary test. If two tests share the same hidden assumption, agreement between them may only prove that they share the same assumption. Independence is about the error mechanisms, not just the number of instruments. This idea appears across engineering. Two thermometers made from the same defective batch are not strong independent confirmation. Two survey measurements using the same incorrectly positioned reference point do not create a correct map. Two software checks that repeat the same mistaken conversion do not protect against that conversion. In Hubble's case, the central risk was an optical reference that appeared authoritative but was not anchored securely enough to an independent physical reality. Another important point is that the mirror's wrong figure did not need to look visibly strange. The surface was polished to a high standard, and its broad dimensions and reflective function were not the issue. The problem was the exact departure from the designed aspheric shape. This is why visual inspection was not a realistic defense. Looking at the mirror could not reveal the problem. A human observer standing near the hardware could not see the wavefront error by eye. Only a measurement system sensitive to the intended figure could do that. The entire case therefore turns on how the measurement system was built, aligned, calibrated, verified, and interpreted. Once Hubble was in orbit, engineers used the telescope's actual optical behavior as new evidence. The images themselves became a large-scale test of the complete system. They showed a repeated blur pattern that could be modeled as spherical aberration. The fact that the pattern was stable helped investigators distinguish it from a temporary focus setting or an isolated instrument fault. It was a property of the telescope's optical path. This is a good example of diagnosis from system behavior. Engineers did not need to see the original manufacturing error directly. They could infer the nature of the upstream problem from how light behaved at the final output. The pattern of the error contained information about the shape of the mirror. The solution also demonstrates a major principle of spacecraft engineering. Sometimes the most practical correction is not to replace the original component, but to add a compensating function around it. Hubble's first servicing mission, carried out in December 1993 by the Space Shuttle Endeavour crew, installed corrective optics known as COSTAR and replaced the original wide-field and planetary camera with WFPC2, which included its own optical correction. COSTAR used small corrective mirrors to compensate for the aberrated light before it reached several instruments. The primary mirror itself remained in the telescope. The correction worked because the optical error was systematic and predictable. Engineers could characterize how the mirror distorted the wavefront and design optics that imposed the opposite correction. This was not a magical repair, it was a carefully engineered response to a measured and stable error. Later Hubble instruments were designed with correction built in, and COSTAR was eventually removed when it was no longer needed for the remaining instrument set. The broader story is often presented as a recovery story, and that is fair, but the recovery should not erase the original lesson. Hubble's serviceable architecture made correction possible. The telescope had been designed for orbital servicing, and that feature created an option when the primary mirror could not simply be taken back to the workshop. This is a systems lesson about risk transfer. A design can reduce one kind of risk by creating another kind of complexity. Servicing adds interfaces, mechanisms, and operational demands, but it can also provide a path to correct hardware that cannot be replaced easily. In Hubble's case, the ability to install corrective instruments changed the practical consequences of the optical error. That does not make the original testing problem acceptable. It shows why resilience begins before anything goes wrong. Now I want to be precise about the evidence boundary. The public facts support these statements. Hubble's primary mirror had spherical aberration. The mirror's figure was incorrect. The reflective null corrector used in its production and verification contained an optical error. The testing process did not prevent that error from shaping acceptance. The problem was identified through on-orbit performance, and corrective optics restored the telescope's ability to produce high-quality scientific images. What I should not do is invent a private conversation, a precise warning that cannot be verified, an unsupported claim about one person's intent, or a dramatic story about hidden information. The engineering case is strong without those additions. In fact, adding invented details would weaken it, because the real lesson depends on understanding the measurement chain rather than turning the event into a morality play. So what should engineers take from the Hubble mirror? First, a test result is only as trustworthy as the complete chain behind it. That chain includes the instrument's geometry, calibration, alignment, reference standards, data reduction, and human interpretation. A clean output does not certify every link. Second, high precision requires independent validation, not just more decimal places. If an instrument is capable of measuring a surface to extraordinary accuracy, its own reference error must be bounded with equal seriousness. Third, a disagreement is not automatically noise. Sometimes an unusual result is the only visible clue that two parts of the measurement system do not agree. The correct response is not always to average the readings or choose the familiar one. Sometimes the disagreement is the result. Fourth, testing should be designed around plausible failure modes. If the main risk is an incorrectly positioned optical element, then the verification plan must be capable of detecting that exact class of error. A test that assumes its internal geometry is correct cannot be the only defense against internal geometry being wrong. Fifth, manufacturing and inspection should not be allowed to form a closed loop around one unchallenged reference. When the same standard guides the process and approves the outcome, an independent standard becomes especially valuable. Finally, the Hubble case shows why systems engineering matters. The mirror, test apparatus, polishing process, software, inspection culture, launch plan, instruments, and servicing architecture were not separate stories. They interacted. A tiny error in one measurement component influenced a major optical surface. The telescope then carried that error into orbit, where the final system exposed it. The correction came from another layer of the system, using the predictable behavior of the first error. That is the full engineering picture. Not a single bad part, but a chain in which assumptions move from one stage to the next. If I had to reduce the entire case to one sentence, it would be this. Hubble's mirror was not defeated by a lack of precision. It was defeated by precision applied to the wrong reference. That is what makes this case so valuable. Modern engineering often rewards numbers, repeatability, and confidence. Those things matter, but they do not answer the first question. Are we measuring the right thing against the right standard? A test can be elegant, sensitive, and consistent while still steering a project away from its real objective. The safeguard is not suspicion of every measurement. It is disciplined trust. Understand the mechanism, challenge the reference, separate independent evidence from duplicated evidence, and treat unexplained disagreement as information. Hubble eventually became one of the most productive scientific instruments ever placed in orbit, but its early optical problem remains a permanent reminder that a test is not reality itself. It is a model of reality built from components, assumptions, and procedures. When that model is wrong, the smartest team in the room can still receive the wrong answer. If you enjoy forensic engineering stories where the smallest component changes the outcome of an entire system, like this video, follow for more carefully sourced case files, and comment with the first measurement you would independently verify before trusting a result as precise as Hubble's.